Hello everyone, I'm Yawei Li from ETH Zurich. I would like to introduce my recent work on network compression, DHP, differentiable meta pruning via HyperNetworks. This is a joint work with Shuhan Gu, Kai Zhang, Luquan Gu, and Radu Timofey. So first of all, the introduction. As well known, convolutional neural networks have achieved state-of-the-art performance in various areas, including computer vision, speech recognition, and natural language processing, and so on. But the advances often come with deep layers, large model size, and huge computational requirements. This has become a challenge for fast inference, model storage, and transmission. So, in order to solve this problem, pruning has become the workhorse for network compression, which aims at a lightweight and efficient model for fast inference. Network pruning methods can be classified into two categories, including unstructured pruning and structured pruning. Unstructured pruning prunes the individual connection between neurons, while structured pruning prunes the whole neurons. In this paper, we focus on structured pruning that tries to prune the less important output channels in the convolutional neural networks. In earlier pruning methods, the pruning ratio for each layer is determined by human experts. The advanced automatic pruning method determines the pruning ratio for each layer automatically. Among the current automatic pruning methods, AMC and meta pruning are two important algorithms. AMC resorts to reinforcement learning to determine the pruning ratio for each layer, while meta pruning utilizes HyperNetworks and turns to evolutionary algorithm to search for the best candidate. But the problem of those algorithms is that the solver, that is reinforcement learning, and evolutionary algorithm is not differentiable. So they need a longer training time until the convergence of the algorithm. In this paper, we introduce a differentiable automatic pruning method, and the contribution is threefold. Firstly, a new architecture of a hypernetwork is proposed. Different from the classical hypernetwork composed of linear layers, the new design is tailored to automatic network pruning. By only operating on the input of the hypernetwork, the backbone network can be pruned. Secondly, a differentiable automatic pruning method is proposed. The differentiability comes with the specifically designed hypernetwork and the utilized proximal gradient algorithm. It accelerates the convergence of the pruning algorithm. Lastly, the potential of automatic pruning method as a fine-grained architecture search is revealed. Next, the methodology. For each layer of the backbone network, a latent vector that controls the output channel of the layer is attached. The latent vector has the same dimension as the output channel. In the forward path, the hypernetwork takes two latent vectors from the current layer and the previous layer as input. After the operations in the hypernetwork, the output is used as the weight parameters of the backbone network. L1 sparsity is applied to the latent vectors and proximal gradient is used to solve the problem. In the backward path, the gradient can be passed from the backbone network to the hypernetwork. Then let me explain the operations in the hypernetwork. First of all, the two latent vectors ZL and ZL-1 are taken as input. The AL controls the output channel of the current layer and ZL-1 controls the input channel. The latent layer computes a latent matrix from them. Then the embedding layer projects each element of the latent matrix into an embedding space. The last explicit layer converts the embedded vectors to the final output. If one element in ZL is pruned, then the corresponding slice of the output tensor can be removed, achieving the effect of network pruning. As said, L1 sparsity is applied to the latent vectors to solve the sparsity regularization problem. Proximal gradient solver is used. Here is a loss function. The L term is a original loss, D is a rate decay, and R is a sparsity regularizer. In this paper, R has a form of L1 norm. The parameters of W and B are updated with standard gradient descent algorithms. The latent vectors are updated with proximal gradient, which contains a gradient descent step and a proximal step. After the optimization, the latent vectors with small magnitude are pruned, and a pruned network is derived. The training of the pruned network continues until the convergence. Next, we show some experimental results. This slide shows the results on MobileNet V1 and V2 for tiny image data classification. The original model with different width multiplier is set as a baseline. The DHP models outperform the original model at all the operating points. This slide shows the results on CFR10 image classification. DHP outperforms the compared methods under comparable model complexity. On tiny ImageNet, DHP shows lower errors than the original model and meta pruning. We also try to replace L1 regularizer with L2 regularizer and kept the same pruning strategy. Compared with L1 regularizer, slightly worse results can be observed for L2. For ResNet 110 and ResNet 164, L2 regularizer leads to results comparable with L1 regularizer, but at a larger parameter budget. Here are more results on ResNet 110 and ResNet 164. When the compression ratio is not too severe, the accuracy does not drop too much. We also conducted experiments on image super resolution and denoising networks. For image super resolution, DHP achieved a significant reduction of runtime. The same phenomenon is also observed for denoising. Here are some visual results. The visual quality of the images of DHP is almost indistinguishable from that of the baseline. Thank you very much for your attention. Welcome to our post session. Code is available, and welcome to my website for more information.